Hello. Hello, everyone. A very good evening to all of you. I hope I am clearly visible and audible to you people. Let me just check once. Yeah, so I am live. Hope all of you are doing great and your preparation for your Re-NEET exam, which is going to happen on 21st of June. It's going good and you're practicing some questions and moving forward and also attempting some mock exams to judge your preparation and check, right? So in our today's video, in our today's class, we will start with the modern physics. We have already completed current electricity. So current electricity as well as modern physics, both these units have a higher weightage as compared to the other topics. They are quite important. They are more important than the other chapters. They have, like, usually every year in your NEET examination, around 5 to 6 questions come from current electricity as well as from dual nature. So first, like, we are covering the high weightage chapters, right? So before starting with our today's class, there's one thing which is being run for you guys right now, and it is a totally free of cost initiative, which is Re-NEET 2026 Reloaded Crash Course. So this is a free crash course. If you scroll down on this page, you will see there is a fees of 0 rupees. This is something which was a paid thing earlier. Like, you can also see the fees of 4,999. But right now, because the NEET exam is happening again this year, so for all the re-NEET students, this is absolutely free. And like, by joining this crash course, the main benefit which you will get is you will get all the schedule for all your classes. You will get the digital study material. You will get all your assignments, class notes, all India test series, everything covered in this crash course. And you don't have to pay for or any of these things. You just need to go to the link in the description below. As soon as you click on that link, you will like, it will bring you to this page. When you click on buy now, it will just ask you to enter your mobile number and other some basic details like your name, your parents' name and phone number. And post that, you will be able to register. So do make sure to check out this crash course, right? Now, moving forward with our today's class. So in modern physics, as you people are already might be aware that mainly there are three chapters: dual nature of matter, atoms and nuclei. Like, sometimes we also keep semiconductor along with these three chapters only. But what I have planned for you people is, first we'll do dual nature, then tomorrow and day after tomorrow, we'll cover atoms and nuclei. And then in the next week, we will start with semiconductor devices. So from semiconductor devices also, every year, at least 3 to 4 questions do come. Okay, so what we'll do for today's session is, first we'll revise the chapter in the first 30 minutes, and then in the later 30 minutes of the class, we are going to practice some PYQs. Okay, so the total duration of the class would be 1 hour, and we'll make sure to practice PYQs in the later 30 minutes of the class. So starting with dual nature of matter, the very first thing which you guys must have studied was photons. So photons were nothing, but photons were just packet of energy. They are just packet of energy, right? And this packet of energy, these packets of energy, they might be emitted from any radiation, like from any source. If we say that anything is radiating energy, then from that particular thing, some photons might be released. So they are just some packet of energies. The more important part was the properties of these photons. The more important part was the properties of these photons. So like we'll quickly revise all the properties and I'll write that in short just for your reference. So the very first property was, like, if you want to calculate the energy of these photons, so you can calculate the energy using the formula E is equals to h nu. H is Planck's constant and nu was the frequency. Frequency is also equal to c by lambda, speed divided by wavelength. So nu is equal to c by lambda also you can substitute. This was the very first property, like that how can we actually calculate the energy of a photon. Then the second property was that all the photons will always and always move with same speed. Like every photon which is present in atmosphere, every photon which is present in air, they all these photons will move with same speed, and that speed will be equal to speed of light, that is c, which is denoted by c, and the value of this c is equal to 3 into 10 raised to the power 8 meter per second, right? So they all the photons will have same speed. Then the third main property was that the velocities of photon will only be different. The velocity will only be different, if you change the wavelength, if lambda is changed. Lambda is your wavelength. If you change the wavelength, then the velocity will change corresponding to the wavelength. But mind it, if on changing lambda, c also changes, speed also changes, then we can say this ratio c by lambda will always be a constant. That means their frequency will always be constant. Frequency will always be constant. Frequency will not change, right? Then the fourth fourth property was how can you actually calculate the momentum. So momentum can be calculated by p is equals to h by lambda. We'll also study this in your de Broglie equation. You people must have already studied this earlier as well. So this was the fourth property, and then the fifth property was the rest mass of the photons is 0. Every photon has 0 rest mass. Each photon has 0 rest mass, right? Like 0 rest mass means they cannot exist at rest. They will only exist in a moving nature. Like you will never ever find a photon stationary, because photons can't actually exist at rest. They will always be moving with some velocity. So these were some of the main properties of your photons, right? Then after understanding photons and their properties, the very next topic which you people must have studied was photoelectric effect. Photoelectric effect. So if I like quickly revise, what was photoelectric effect? So photoelectric effect, it was just a phenomena that you have a piece of metal, and whenever this metal is irradiated, like whenever any form of energy or any form of radiation is incident on this piece of metal, this piece of metal will release some electrons, or to be precise, they will also release some photons, some packets of energy. So this was just the concept of photoelectric effect, that whenever a high frequency light or whenever a particular radiation falls on a piece of metal, the metal will emit some electrons. But there was some condition. There was some condition for the emission of this electron. What was the condition? That if the frequency of this radiation, this incident radiation is nu, and this metal will have some work function, which we denoted with W naught. So basically what you need to understand is that like in this box there is around like I'll just take an analogy, and that analogy might be that the weight of this box is, the mass of this box is 100 kg, and there is a boy whose mass is the body mass is 40 kgs, let's suppose. And when we are playing this game, that this boy has to come and lift this box, and the only condition is that any person can only and only lift a box when their weight is either equal to the weight of the box, mass of the box, or more than that. a person whose mass is less than the mass of this box cannot actually lift that box. So what do you people think, that can a 40 kg boy, a boy having 40 kg of mass, can he lift 100 kg? No, because 40 is less than 100. So what will be the condition then? At least the mass of this boy should be 100 kg, only then he will be able to lift it. But if his mass is even more than 100, let's suppose 110, even then he can lift this box, right? So the a similar sort of a situation happens over here. So what you have to understand is that work function, it is basically the energy which is required to break the bonds of this electron. At the end of the day, our goal is to release or emit some electrons, right? And that electron is already bounded with some other electrons and some other atoms within the metal, right? So to emit the electron, to release the electron from this piece of metal, we say that we need this process. For example, this is an atom, this is the electron which you need to emit, and this is the other atom. So this work function, it is basically that energy which is required to break these bonds. This energy is actually used in breaking these bonds. It will not be a part of the released electron. So using this work function, we say that if the threshold frequency of this metal is nu naught, then the only condition under which electrons will be emitted was that incident frequency should be greater than the incident wave threshold frequency. Nu should always be greater than nu naught. Only and only in that case electrons will be emitted, right? And then there were two conditions, that if this incident frequency is equal to the frequency, like the threshold frequency, in that case electrons will be emitted, because like the same case, if boy is also 100 kg and box is also 100 kg, but these electrons will be released with zero velocity, their speed will be zero. If the frequency of incident radiation is more than the threshold frequency, particularly in this case, the electrons will be released with some kinetic energy, with some velocity, right? So there were two formulas. First was the Einstein's photoelectric equation. What did Einstein's photoelectric equation exactly tell us? Einstein's photoelectric equation said that you can calculate the energy of any emitted electron using the formula E is equal to h nu, like the same formula which we used for a photon. And this E is equal to h nu energy. This is the total incident energy. This is used in two ways. First, a part of it is used in overcoming the work function W naught, and the remaining part of it is used to impart the kinetic energy to the emitted electron. Okay. This work function, we can also write it as h nu naught, where nu naught is the threshold energy. Threshold frequency. So h nu is equal to h nu naught plus half mv square. And then when we transpose this term over here on the other side, we can say half mv square is equal to h nu minus h nu naught. Then h can come out as a common, nu minus nu naught. And this half mv square is actually equal to the kinetic energy of the emitted electron. This is actually equal to kinetic energy of emitted electron. So basically our equation was that kinetic energy is half mv square, and half mv square can be calculated by using h nu minus h nu naught. So most of the times what we are given in the question is incident frequency, the frequency of the incident radiation, and the threshold frequency. And then we are supposed to calculate the velocity with which electron is emitted, right? So we can simply do that. M is the mass of electron, V is the velocity with which electron is emitted. Moving forward, there were four laws of photoelectric emission. Four laws of photoelectric emission, right? The very first law stated, like if you people don't have any notes or anything where you have already written the laws, then what you can do is you can just like I'll dictate the complete law, you can just pause the video and then note it down, right? So the very first law stated that the number of photoelectrons ejected per second is directly proportional to the intensity of the incident light. That means if I take the number of electrons over here, or the photoelectric current over here on y-axis, and the intensity of my radiation on the x-axis, then we can say that they are directly proportional. Law just stated that number of photoelectrons ejected per second is directly proportional to the intensity of incident radiation. Higher the intensity of incident light, more photoelectric current and more number of electrons will be ejected. This was the very first law. Second law stated that the complete process is very instantaneous. Instantaneous basically means that as soon as a radiation is incident, as soon as a radiation is incident, quickly, like instantaneously, a electron will be emitted or a electron will be released from that very metal. So it is an instantaneous process. The time lag between the incidence of radiation and the emission of photoelectrons is very negligible. It is very, very, very small, approximately of the order of 10 raised to the power minus 9 seconds. Then the third law stated that for every given metal, there is a minimum frequency. There is a minimum frequency of incident radiation which is required, and below that incident frequency, the emission of electrons will not take place. And that minimum incident frequency, the name of that minimum frequency was threshold frequency. The same thing which I just discussed with you people, that we will actually require some extra energy which will be used to break the bonds of the electrons. Then the fourth law stated that the maximum kinetic energy with which the electrons are emitted from a metal surface is independent of the intensity. So basically we are saying that kinetic energy is independent of intensity, but kinetic energy does depend on the frequency, as we saw from the formula. Kinetic energy was simply half mv square, and half mv square was actually equal to h nu minus h nu naught. So it is, the kinetic energy actually depends on frequency, but it does not depend on the intensity, right? So these were the 4 laws of photoelectric emission. Then there was something called as a stopping potential. So stopping potential actually meant that the amount of potential which I have to apply in order to stop this electron from being emitted. So it is a negative potential which has to be applied externally on that metal in order to stop the electron from being emitted. That was stopping potential. Then we had 3 graphs. First graph was, like, both the first 2 graphs are this like y and x axis quantity is same. On y axis we have photoelectric current, and on x axis we have stopping potential. The first graph was like this, right? And this graph was actually made for, like, this will cut x axis over here. The intensity of this is I2, this is I1. I2 is greater than I1. This is basically the graph between photoelectric current and potential. When frequency is constant, intensity is different. Frequency is constant and intensity is different. So we fix the frequency, but we change the intensity. First time the intensity is I1, second time the intensity is I2. So we see these 2 graphs, and the graph which lies above has a greater intensity. I2 is greater than I1. The second graph is just opposite of this. Like in this graph, we kept frequency constant, intensity different. In the second graph, we say intensity is constant, frequency is different. The graph is same. On y-axis, we have photoelectric current, and on x-axis, we have potential. The graphs were something like this. So you just have to remember that whenever the graph becomes parallel to x-axis, it basically represents the both. It will like be parallel to the for a particular set of for a particular value of intensity. This over here was called V naught, the stopping potential, the minimum potential. This was your VO1, this was VO2. This is for frequency nu1, this curve, and this curve was for frequency nu2. And over here, nu2 was greater than nu1, and intensity was constant. I was constant. So these were the first two graphs. The graph for photoelectric current and versus potential. First time when frequency is constant, intensity is different. Second time when frequency is different, intensity is constant. Then the third graph was for stopping potential. Third graph was for stopping potential on y-axis and frequency of radiation on x. Frequency of radiation on x-axis. Okay, and this graph was a straight line graph like this, and it started from like it does not start from origin, but it starts from some other point. And why does this start from here and not from origin? Because this initial frequency, this is basically your threshold frequency nu naught. So this third graph will look like this. I hope all the three graphs of photoelectric equation are clear. Like, we're just revising it quickly because this is supposed to be a one shot or a revision sort of a lecture, and we have to devote like more time for the question practice. Now, can anyone confirm like, or can anyone like answer in the chat that photoelectric effect denoted or depicted which nature of light, particle nature or wave nature? Photoelectric effect depicts which nature of light? Is it particle nature or is it wave nature? Yeah, in case you have any doubts, then you can post your doubts in the chat section. You can post your doubt in the chat. I'll discuss that. By the time, like, can anyone confirm me or can anyone answer that photoelectric effect depicts which nature? Photoelectric effect depicts which nature? Is it particle nature or is it wave nature? So photoelectric effect basically depicts particle nature of light. Photoelectric effect depicts particle nature of light. Okay. So this was particle nature. So photoelectric effect depicted particle nature. Then which effect depicted the wave nature of light? So de Broglie hypothesis basically depicted the wave nature. De Broglie hypothesis. Like, you have to remember these kind of things, especially for your statement based questions. De Broglie hypothesis depicted wave nature of light. So what did de Broglie say actually in his hypothesis? De Broglie basically said that sometimes a moving particle will behave as a wave and sometimes it will behave as a particle or a wave associated with a moving particle. And he said that the wave associated with a moving particle can actually be called a matter wave or a de Broglie wave. And then he also calculated the wavelength of that matter wave or de Broglie wave. And then that formula was, that wavelength was called de Broglie wavelength. That wavelength was called de Broglie wavelength. And de Broglie wavelength, for the formula came from E is equal to mc square, and E is equal to mc square, and E is also equal to h nu. When you use this, you can just replace nu with hc by lambda. Lambda was the de Broglie wavelength, so lambda came out to be h upon mc, or m into c is basically momentum, so the formula came out to be h upon p. De Broglie wavelength is simply equal to Planck's constant divided by the momentum of the particle, right? And then there was one important thing, which was de Broglie wavelength of a electron. So for a electron, for a particular electron, if you want to find the de Broglie wavelength, the formula for de Broglie wavelength of an electron was h upon root 2 MeV. Capital V is the potential difference, E is the charge on one electron, M is the mass of one electron, H is the Planck's constant. And when you put the value of root 2 Me, this will come out to be, sorry, this, and H also, you can put the value of H. This comes out to be 12.27 divided by under root of V in Armstrongs. This value is in Armstrongs. So this was all about de Broglie. So in this chapter, there are mainly two major things from which numericals come. First is your photoelectric effect, and second is your de Broglie hypothesis. Then there was something called as Davison and Germer experiment. So Davison and Germer experiment, it basically they basically drew a graph between the angle and the intensity of scattered electron, and then using that experiment they found out that at a potential of 54 volts the intensity of radiation was maximum, right? And the last two things in the chapter were Herd's observation and Linard's observation. So both these observations basically depicted the particle nature of light. So from the point of view of numericals, like if you haven't really studied your modern physics, or if you're not very confident, then my advice would be these are very scoring chapters. You just need to remember two formulas and you will be easily able to solve 70 to 80% of the numericals because they are from the same formula. First is the photoelectric equation and second is the de Broglie wavelength. Even if you remember both of these, you will be able to solve 60, 70, 80% of the questions easily. So just remember both these formulas and then we'll move towards the questions, the PYQs. By that time, if anyone has any doubt, then you can post in the chat. Yeah, so we have a doubt. So, okay, so it is basically from current electricity. No problem, I'll take it. So the doubt is that if three bulb of same power rating is connected in series, so basically we have three bulbs means we have three resistors of same power. Let us suppose the power of these three is P, P and P. Same power rating connected in series, which bulb will glow brighter and why? So what you have to do is you just have to remember, if you have attended my yesterday's or day before yesterday's live lecture, I discussed that there are three formulas for power. First is V into I, second is I square R, and third is V square by R. You just need to remember one thing when you are trying to compare power, especially in series or parallel. What you need to see is that in series, the current remains same. Current is same, but potential is different, right? In series the current is same but potential is different. So if you use the power formula of V into I, then your I is same, power is same, V is different, this V is different. Now because the current for all the bulbs is same, so each and every bulb will glow with the same brightness. Each bulb will grow with the same brightness because the current through each bulb is same. I hope I have answered your question. I'll just wait for a minute. If anyone else has any doubts, then they can post in the chat and we'll take those doubts before moving to our PYQ practice questions. If anyone has any doubt, then you can just post it in the chat. Okay, so I suppose no one has any doubts. I hope, Swasti, I have answered your question. I've cleared your doubt. So now moving forward to the PYQ practice. So for like we all will always keep on practicing PYQs within the class, but like you also know, like there are some constraints and there are some limitations on the number of questions that we can actually do within the class. So for your extra practice, there is something called as Vedantu NEET AITS 180 test series, which is launched by Vedantu especially for your Re-NEET examination. And this complete test series is actually designed by subject experts, right? So, like you can just, we have posted the link for this AITS in the description below. You can check this out. Within in this test series, you will also get 3600 plus MCQs. You are getting 12 full and 8 part syllabus mock tests. So it will actually help you in doing a very good practice of questions. So do make sure to check this out as well. Also make sure to check out the free crash course, free Re-NEET reloaded crash course. And mind it, like just I'll just reiterate the same point that this crash course is being offered for free exclusively for you people. Otherwise, like it was something which was paid and the fees already you can see, but right now it is just being offered for free. You don't have to pay anything. So do make sure to check out both of these things. You can find the link in the description. Okay, now moving to our PYQ questions. So, what I usually do in my classes is that I'll just show one question on the screen. Then I will give you 1 minute time. You will have to solve the question and post your answer in the chat. You can just type in your option out of ABCD, which option you feel is correct, and then we will discuss that question afterwards. Like after that 1 minute is over. So we'll start with the very first question. So this is a 2022 question. You have 1 minute to solve this. So I'm expecting some answers in the chat. If you just need to write A, B, C, D, whichever option you feel is correct. That would work. Any answers? You're just given the threshold frequency. The question is saying that the threshold frequency of a photoelectric material is nu naught. And if the light of frequency 4 nu naught is incident, maximum kinetic energy you have to calculate. It is a like pretty straightforward formula based question. We just discussed kinetic energy is equal to h nu minus h nu naught. H comes out to be common, nu minus nu naught, right? You're given the you are given this. Yes, so I see a correct answer, option number C. So h 4 nu naught minus nu naught. So 3h nu naught will be your correct answer. Right. Option number C. Moving forward to the next question. So this is your second question. This is also a 2022 question. So I see many doubts regarding your KCET results. So like Jasmine ma'am must have discussed that with you. You will also see a video as soon as the results are released. We are also waiting for the results, and the results are expected to be out soon. So like usually it comes in the very first week of June. So I'm sure as soon as your results are released, Jasmine ma'am will see you, right? Okay, so there is one answer which says option number B. So what does the question says? Question is saying that light rays of photon energy 4.2 eV, light rays of photon energy 4.2 eV fall on a metal surface of work function. So your light rays of photon means this is the energy of incident. This is the energy of incident radiation. Like this is the incident energy. And then you are given the work function of the metal 2.2 eV. You just need to find out the stopping potential. Again, the same formula. E is equal to, kinetic energy was equal to h nu minus work function, right? So you are just asked the potential, the stopping potential. So stopping potential and kinetic energy, if you want to relate, kinetic energy will be equal to charge multiplied by the potential, stopping potential. So we are given the energy of incident radiation, which is 4.2 eV, minus work function is 2.2 eV. Both these things are in electron volt. Volt means this small e denotes the charge on one electron in eV. So this is equal to q into v. So q into v comes out to be equal to 2 eV. Charge on one electron, charge on photon is equal to E. So E gets cancelled out with E, and the remaining stopping potential is equal to 2 volt. Yeah. So Ruchita, your answer was correct. Option number B. Moving forward to the next question. Question number 3. So in this question, you're just given that a EM wave of wavelength lambda is incident on a photosensitive surface of negligible work function. The surface is photosensitive and negligible work function means you can take the work function to be zero, negligible. Then the question is saying if lambda d is the de Broglie wavelength of emitted photoelectron, then you have to find out the relation between de Broglie wavelength, lambda d, and wavelength of incident radiation lambda. Just need to find out the relation between that. So you can just use both those formulas, first for the kinetic energy and second for the de Broglie wavelength. Then you will be able to get the correct answer. Okay, then we'll discuss this question. So we basically know kinetic energy is equal to h nu minus work function. Work function is 0, so it is simply equal to h into nu. Frequency nu is equal to c by lambda, hc by lambda, right? And then de Broglie wavelength lambda I can substitute by h upon p. So simply if I just substitute this over here, then I will get p square by 2m. This equal to p square by 2m, and from here I get momentum is equal to root 2mhc by lambda, right? Momentum comes out to be equal to this. Then de Broglie wavelength lambda d is equal to h by this p, this momentum. So h divided by root 2mhc upon lambda. Then so like none of these answers is in roots, so under root. So what I need to do, I need to just square it. If I do whole square, I'll just write this again. If I just do whole square of the complete thing, then I will get lambda d square is equal to lambda d square will be equal to h lambda upon 2m c. One h gets cancelled with the h inside the under root, and the above h gets squared, so 1h is left, h lambda by 2mc. And from here I can write this is equal to, I just need to rearrange, I just need to find lambda. So lambda is equal to 2mc upon h lambda d square. So this should be our first option, option number A. Moving to the fourth question. So I need to see some answers in the chat quickly. So you just have to make sure that you keep your spirits high and you keep your motivation high. I know a lot of things are going on around us, around you people especially, and you must be anxious. But in these times also, because your NEET exam is just 15 to 16 days away, right? The paper is on 21st. It's already 3rd, so you don't have much time left. Whatever happened was very unfortunate, but right now we don't have any other option than to study. So do make sure that you study with all the hard work and you gather all your energy and just put in everything in your studies right now. So like, even if you join the daily live classes and you do make sure to solve the questions which you do in the class, even that will be a good practice for you. Because like, we usually do PYQ questions only in the class. Like, this is a 2021 question and similar questions will come. So for fourth question, what we are given? We are given the number of photons ejected per second. The question says the number of photons per second emitted by a monochromatic source of wavelength. Wavelength is given, lambda is given, delivering 3.3 into 10 raised to the power minus 3 watt is. Okay. So you are basically asked to calculate the number of photons ejected per second. So the formula for number of photons ejected per second is basically power divided by energy. So basically you need to remember that power is basically number of electrons ejected per second, number of photons ejected per second into the total energy of single photon. So number of photons is P by E, power divided by energy. And energy we can calculate by h nu, and nu we can write as h c by lambda. So lambda goes above. Now we just need to put in the values. Power is 3.3 into 10 raised to the power minus 3. Wavelength is 600 nanometer. We need to convert it into meters. So 10 raised to the power minus 9 divided by value of Planck's constant is given 6.6 into 10 raised to the power minus 34 into speed of light is 3 into 10 raised to the power 8. You just need to simplify this. So this simply becomes 2. This is 2 3s are 6 and this becomes 100. So like, if you see in the numerator, your power becomes 10 raised to the power 2 into 10 raised to the power minus 12 divided by 10 raised to the power minus 26. This 10 raised to the power minus 26 goes above. It becomes 10 raised to the power minus 10 plus 26. So 10 raised to the power plus 16. Option number A will be your correct answer. So this is the same calculation which we discussed. Moving forward to the next question. So for this question, you're simply given a proton and a alpha particle that they are accelerated through the same potential. Why are they saying same potential? You just saw I shared a formula for electron. Like formula was H upon root 2 MeV. So this capital V is same. They are accelerated through the same potential difference. You just need to find out the ratio of their de Broglie wavelengths. So this was a de Broglie wavelength for a electron. This was the formula for a electron. If I need to find out the de Broglie wavelength for a proton, then I'll just write lambda p, and this lambda p is equal to H upon root 2 MQV divided by lambda alpha. Like alpha, the wavelength of alpha particle, it is H upon root 2 MQV. So this is the, over here we have to take the mass of alpha particle, charge of alpha particle. H gets cancelled with H, root 2V gets cancelled with root 2V. We are just left with under root of mass of alpha particle, charge on alpha particle divided by mass of proton into charge of proton. So when you substitute, so this will come out to be under root of 8. You just need to put in the values. This will come out to be root 8. Root 8 you can simplify as 2 root 2. So the answer should be 2 root 2 is to 1. That is option number C. Please be very careful when you're choosing the answer, and especially if you see two similar options like over here C and D. A very small mistake, like if by mistake you took lambda, the wavelength of alpha particle above, you will straight away lose 5 marks. Why do I say 5 marks? 4 marks for the correct answer which you were supposed to get, and -1 which you lost due to the negative marking. So you just need to make sure that you choose the right answer whenever you see these type of options. Moving forward to the next question. Yeah, so Ruchita, we also have 2026 questions in between. Uh, so don't worry about that. Can I see some answers in the chat quickly for this question number 6? Question number 6 simply says that light of frequency 1.5 times the threshold frequency. So we can just consider that if threshold frequency is nu naught, then incident radiation has a frequency of 1.5 nu naught. Incident on a photosensitive material, if the frequency is halved and the intensity is doubled. You just need to tell the effect on the photoelectric current, right? So we already know that the photoelectric current, it is basically independent of the intensity, right? The photoelectric current, it only and only depends on the frequency, and we say that frequency is halved. So when frequency is halved, energy is also halved. So energy, earlier the energy was 1.5 times nu naught into h. H is a constant, so we can just like keep it aside. 1.5 divided by 2. So 1.5 divided by 2 now becomes 1.75 nu naught. The problem is now the incident radiation has 0.75 nu naught, but the threshold frequency is nu naught. Now, as this incident, the frequency of incident radiation is less than the cutoff or threshold frequency, so no emission will take place. If no emission takes place, then photoelectric current will be 0. Option D will be your correct answer in this case. Next, question number 7. For question number 7, you can just directly use the formula which I told you a while back. The de Broglie wavelength for an electron, 12.27 upon root V in Armstrongs. 12.27 divided by under root of potential difference V. So using this formula, you will get the value of de Broglie wavelength in Armstrongs for electron. This formula is only and only applicable for electron. Remembering these like shortcut formulas and some short tricks, some shortcuts, that will actually help you in saving a lot of time while doing numericals. The time which you save from here, you can actually devote the time in revising your paper, and you can invest that time on some very difficult questions which might be there in your exam. Okay, so we'll discuss this question. The question says an electron is accelerated through a potential difference of 10,000 volt. Its de Broglie wavelength is. So now, because I have a shortcut formula already and I remember that formula, I don't need this information, right? I can directly use my formula that wavelength for electron is 12.27 divided by under root of V, and I'll get my wavelength in Armstrongs from here. So under root of 10,000, it will basically be 100. So this will be 12.27 divided by 100. 100 means 10 raised to the power. I can just cut 100 from here and write 10 raised to the power minus 2. This is in Armstrongs. Armstrong is 10 raised to the power minus 10. So answer will be 12.27 into 10 raised to the power minus 12 meters. Option number B. Now, you see, like we are able to solve this question quickly in just 2 steps, just because I remembered this formula. If you go through the whole process, like you just start your journey from lambda is equal to h by p, you put p as m into v, then you use the formula for kinetic energy, then you substitute that in terms of potential, then you will, like you will end up wasting a lot of time in coming to this formula. So it's better, like you should, directly remember or memorize these type of formulas which are mostly used. Moving to the next question. So if you guys quickly answer to the questions, then we'll be able to cover a greater number of questions. Like for today, although I have a huge number of questions, but at least I target to cover till question number 15 for our today's live. Any answers for this question number 8? Okay, so question number 8 says that when light of frequency 2 nu naught is incident on a metal threshold nu naught, the maximum speed of photoelectrons is v1, right? So we are basically trying to say that, like, I'll just use the same formula. Kinetic energy is half mv square, and this kinetic energy is equal to h nu minus nu naught. So for the first scenario, what the question is saying, that half m v1 square is equal to h2 nu naught minus nu naught, that is equal to h nu naught. Then the second the second line in the question says with frequency 5 nu naught, it becomes v2. That kinetic energy becomes half m v2 square if incident light has a frequency of 5 nu naught instead of 2 nu naught. 5 nu naught minus nu naught, this is equal to 4h nu naught. You need to find out the ratio of v1 by v2. I'll use some other color. I can just simply divide these two equations. Sorry. I can just simply divide these two equations. Half m gets cancelled with half m, h gets cancelled with h, nu naught gets cancelled with nu naught. I am left with, sorry, not nu, V1 square by V2 square, and on the RHS, on the right hand side, I am left with 1 upon 4. I was supposed to calculate. Now, what usually happens is, in a hurry and in the pressure of exam, you will just straight away take option number B, and that will cost you 5 marks in your exam. So we have to avoid these sort of mistakes. We need to read the question properly. 1:4 is the ratio of square of velocities. We were supposed to calculate V1 is to V2. So for V1 is to V2, you just need to take square root on both sides. The ratio will come out to be 1:2. That is option number A. So like, whenever you see these such type of easy questions, you don't just directly jump to the answers or jump to the conclusions. That might cost you your marks. Just make sure that you read the question very properly and with a very calm mind. Okay, so I'll just straight away discuss this question because it also uses the concept of one other chapter. So, like, you can just read the question. We are asked the de Broglie wavelength of a neutron in thermal equilibrium with heavy water, temperature T, mass m, K is the Boltzmann constant. You just ask the de Broglie wavelength. So what you need to remember is that thermal kinetic energy is actually is equal to 3 upon 2 kBT. This was the formula which you studied in your class 11th in thermal properties, right? Where Kb was the Boltzmann constant. So over here it's just mentioned K. So K into T, this is the kinetic energy. We are supposed to find out the de Broglie wavelength. So de Broglie wavelength, you just need to remember that kinetic energy is equal to P square by 2m. The formula for, like, this is the relation between kinetic energy and momentum. Kinetic energy is half mv square. If you multiply and divide by mass, this becomes m square v square. So this becomes p square by 2m. This is the relation between kinetic energy and momentum. Sorry. So it becomes p square by 2m. And now we just have to substitute p. So wavelength is basically h by p. You can just substitute p from here. So p is basically root 3 by 2 kt into 2m. 2 gets cancelled with 2, under root of 3 ktm. 3m kt, whatever you can say, h upon root 3m kt. Option number B will be your correct answer. Moving forward to question number 10. So, like, as we are running short of time, so for question number 10, you're just given an electron of mass m and a photon have the same energy E. You have an electron of mass m and a photon, and both these things have the same energy E. Then you are you're asked that the ratio of the de Broglie wavelength of the electron to that of the photon is. We just need to find out the ratio. So de Broglie wavelength of photon, we can simply say it will be equal to hc upon E, right? hc by E, and for electron it will be equal to h upon root 2m E, where E is my energy. Okay, so when I need to take the ratio lambda E by lambda pH, pH is basically denoting photon. This ratio will come out to be E divided by C under root 2m E. So ratio will be, your ratio will come out to be, when you simplify this, root E, this becomes root E square. So 1 E gets cancelled with E. So the ratio becomes 1 upon C under root E upon 2m. Option number B will be your correct answer. Any answers for this question? Okay. So the question says that a metallic surface gives a stopping potential V at wavelength lambda and V by 3 at wavelength 2 lambda. So we just simply know E into V is also equal to kinetic energy. V is the stopping potential, is also equal to H nu minus nu naught, right? Or we can just simply write energy, incident energy minus work function, right? So in the first part, we are given the stopping potential is V when the wavelength is lambda. So I can just simply write hc by 2 lambda minus work function. Sorry, hc by, not this. This is for the next. E nu is equals to, sorry, EV is equals to hc by lambda minus work function. Then for the second part, we are told that when the potential is V by 3, wavelength is 2 lambda, hc by 2 lambda minus work function. You are just asked what is the threshold wavelength for the surface. We just need to calculate the threshold wavelength. When we solve both these equations, we'll get lambda naught, phi naught, that is work function, is basically equal to hc by 4 lambda. You need to solve both these equations. When we solved it, we get the work function as hc by 4 lambda. Work function is equal to hc by lambda naught. Hc gets cancelled with hc. Lambda naught is the threshold wavelength. Threshold wavelength comes out to be 4 lambda. Option number C. Then question number 12. Okay, so like this is going to be the last question for our today's class. So this question states that photons of energy 5 eV are incident on a cathode C. Maximum energy of emitted photoelectrons is 2 eV. When 6 eV photons are used, no photoelectron reaches anode A if the potential of A relative to C is. We are told that when 5 eV photons of energy 5 eV are incident on cathode C, maximum energy of emitted photoelectrons is 2 eV. Then you are said if 6 eV photons are used and you want that no photoelectron reaches the anode, then what should be the potential according to you between anode and cathode? We need to calculate that. So we can simply say that work function over here, if you are saying incident energy is this is E, and energy of emitted photon, basically kinetic energy, is this. So we know kinetic energy is equal to energy minus work function. So work function is simply E minus kinetic energy. Energy was 5, kinetic energy was 2 eV. Work function comes out to be 3 electron volt, right? Work function comes out to be 3 electron volt. Now work function, if it is 3 electron volt, then work function basically tells me that if I apply the same amount of potential, if I apply the same amount of energy from outside in the opposite direction, like if I apply a external potential, then it will stop the photoelectrons to be emitted. Over here, can I say that E is the charge and 3 volts should be the potential if energy is 3 eV, right? That means 3 volt is the potential. Now, we are asked the potential between A and C. So that should be the stopping potential. Stopping potential is negative because it has to be in the opposite direction. So stopping potential over here should be minus 3 volts. That should be applied. So answer should be minus 3. There will be some confusions regarding minus 3 and plus 3. Our answer is plus 3 volts. Plus 3 volt is in the work function. Plus 3 volts is the potential inside the metal. Now when you need to stop the electron from coming out with 3 volts, you need to apply minus 3. You can just simply understand with the help of vector that 3 volt is plus 3 is towards outside. When you need to put the electron inside, then you need to apply the force in opposite direction. So the minus sign comes. Just the sign will be inverted. If this would have come out to be minus 3, then stopping potential would have been plus 3. But that would not be the case because stopping potential is always a negative potential. So this was our last question for our today's class. Again, before closing the session, do make sure to check out both the initiatives which are run by Vedantu right now. So first is your Re-NEET 2026 Reloaded crash course, which is just being offered for free for a fees of 0 rupees. Do make sure to check it out and do register for this crash course. It will not cost you anything. It is just free, absolutely free. Second is the Vedantu NEET AITS test series. In this test series, you are getting total 20 tests, 12 full and 8 part syllabus mock tests, as well as 3600 plus MCQs along with your OMR sheets. So this test series will actually help you with the practice of your Re-NEET examination. So that was all for our today's session. I hope you enjoyed the today's class. If you enjoyed the today's class, then do hit the like button, and you can also leave some of your suggestions or your feedback in the comment section. If you want me to cover any specific chapter earlier or you have any doubts, then you can just post those things in the comments and I will try and resolve those things as quickly as possible. But do make sure to leave in your suggestions if you especially need me to cover any specific topic earlier, so that like we can plan the topics and classes accordingly. Thank you so much for watching today's class, watching today's video. See you in the next session.